Hello, everyone. Welcome to my talk. Today, I'm going to be talking about large-scale geospatial indexing and analysis on Apache Spark. I'm Felix, VP Engineering here at SafeGraph, a data company. So about myself, like I said, I'm VP Engineering at SafeGraph. Before then, I was at Uber running a bunch of data platform teams. I'm currently deeply involved in Apache Software Foundation. I'm a member there. I'm also part of project committee for Apache Spark, Zeppelin, Superset, and Apache Incubator. I am, among other things, a mentor of the Apache Sedona incubating project, which I'm going to be covering today. Aside from that, also mentoring other 6 projects. So today we're going to be diving into a number of different topics. To begin with, we're going to talk about geospatial data, and then we're going to dive somewhat deeper into the distributed processing methodology. And next, we're going to move on to a number of use cases. We're going to cover the actual code, how that could be implemented. And then we're going to wrap up this conversation by talking a little bit about the overall architecture here at SafeGraph. So first, geospatial. So SafeGraph is just a data company. It's fully remote. It was founded in 2014, and the founders have deep connection experience with data and privacy. SafeGraph is a data company. Our mission here is to focus on powering innovation through open access to geospatial data. And we aim to be the source of truth for physical places. One of the key products we have, SafeGraph patterns, provide a window into customer or consumer behavior. It has a very accurate and aggregated foot traffic view by anonymizing millions and millions of devices. Along with it, we have 8 million points of interest of places and businesses where people are spending time. And lastly, we provide these data set in an easy to consume form, and especially as download, CSV file download, and among other different ways that we support. When we think about a SafeGraph product, there are generally 3 different suites. On the left-hand side, you see there are core places. These are the places where people are spending time or money. And then in the middle, you see geometry, which is the building footprint and the spatial hierarchy and relationship between these businesses that like a bounding polygon around these businesses. And then lastly, but not the least, on the right-hand side, you see the patterns product, which, as I described, are about the foot traffic panel. And all of these can be joined by a concept called place key with third-party data, which I'm going to cover a little bit later today. So what are the common use cases with something like this? So on the left-hand side, you see very popular use cases around equity due diligence. And then moving further on the right, you see retail and real estate, and site selection is extremely popular. In addition to that, you can also have competitive intelligence, right? Looking at who is popular, what businesses are your competitor in this space. And then moving further on the right, you see a little bit more of the conventional marketing and advertising, including visit attribution, location-based advertising. And then on the far right, you see the conventional GIS professional type of use cases. But going further, what is geospatial data anyway? The term geospatial describes data that represent features and objects on the surface of the Earth. So these are data that has individual record. We have locational information tied to them, such as coordinate, addresses, city, or postal code. Well, but you can't really have where without what and who. So oftentimes these are all closely tied together. And so you have demographic information that's tied to the location as well. They oftentimes look at together. What are the key challenges with geospatial data though? Well, so for one, it's actually, Earth is really large. It has over 197 million square miles of surface area. So just computing where it is could be expensive. And scaling the computation is actually one of the most challenging aspects of it. And secondly, there is a lack of source of truth. There isn't really a true set of lists of all the possible places you can find on Earth, right? And so oftentimes a partitioner in this space has to go like basically cross-check and reference everything, kind of really know what is the freshest, what is the most correct data set that can be representative of what is going on. And what is going on is really the more interesting, the most challenging part of it. As you know, the world is changing, like things are closing, opening, and is evolving like pretty quickly. And oftentimes really having the right data means that you have the right fresh data. There's also like a real world constraint you have to work with, like how far these things are. You can't possibly have two businesses stacking on top of each other, right? All sorts of things that you need to consider when you're processing geospatial data. So now processing. What does processing mean? So there are historically a number of like kind of tool and framework and services you can use. On the left-hand side, you see ArcGIS, very popular GIS tool. There's this alternative, QGIS, on the right-hand side. You also have, if you are a big fan of databases, right, PostGIS. It's like GIS extension to Postgres, very popular. However, there are a number of limitations of it. Oftentimes, these are single machine implementation, right? Even if you are connecting to it through a distributed system, it takes a lot of work to like connect to the system. There's oftentimes a limitation number of connections you can have. It takes time to execute a query. There's also limitation around it. So in the last 3 years, there's been an advent of like new kind of technique and strategy in terms of processing geospatial data. One being like parallel execution or using GPU to accelerate. So today I'm going to talk about distributed execution. And to do that, I want to run through a quick introduction about Apache Sedona incubating. So it started in 2015 as GeoSpark at the Arizona State University. It's a cluster computing system for processing geospatial data by building and extending on top of Apache Spark. What are the key components of Apache Sedona? Well, first for one, it has an extension to the Spark RDD construct. It also has support for spatial SQL, so you can do spatial query with it. It supports complex geometries and trajectories. It has spatial indexing, spatial partitioning. It also supports a variety of coordinate reference systems. And last but not least, it also has support for high resolution map generation. Here's an example of it. Here, what you see here is a visualization of billions of objects using a component called Sedona Vis. It has function like ST pixelize and ST render that generate images like this. So what are the key advantages of Sedona? Well, it's not limited to these three I have, but I like to focus on these three in this talk. So first of all, spatial query, indexing, and partitioning. And with all of these, what we're seeing here with Sedona is actually 2 to 10 times faster execution and 50% reduction of memory consumption compared to other Spark-based geospatial systems. So what is spatial SQL? SQL is highly popular. If you know about SQL, this is very intuitive. It comes naturally to you. It's an extension to the SQL syntax by implementing two open standards. The first one is Spatial 3. The second one is OGC simple feature for SQL. What it also supports is geometry data types like point, lines, multi-line, polygons. And with that, you can express relationship between the geometry data types. So what you see at the bottom here is a great example of it. You can find all the superhero within the city of Gotham. Another thing I want to dive into is the spatial SQL optimization. Won't go into the specific details here, but there are a number of innovation and optimization with the Sedona framework. It includes range query, join query, KNN join, and also optimize like spatial join strategy. It also supports a variety of data format. So it could be well-known text, WKT, Wicked, GeoJSON, shapefile, so on and so forth. And also support geospatial geometry, like specification, like polygon, like the definition as a string, all these processing. Now we move on to spatial indexing. What is spatial indexing anyway? In simple term is you divide the service up into these area and region, and then you build up a tree, what you see at the bottom. It allows you to do a super fast lookup by basically walking through the tree. And by implementing our tree and quad tree, what the framework has seen is like a substantial improvement in local performance. So if you look at the reference, which is the bar in red, compared to our tree and quad tree implementation, you see that it's basically a third of the execution time. And then you have spatial partitioning. No doubt you will figure, like you probably figure at this point, like partitioning is essential to distributed processing. So the strategy we're having here with Sedona is by kind of really focus on spatial proximity. The logic is as follows. First step, it takes a sample of the data set, all the data points, use the sample data point in step 2 to build the indexing tree that we talked about just now. And then the leaf node we see at the bottom of that tree becomes the global partitioning mapping. And there are different strategies in terms of what tree you're going to employ for the partitioning scheme. It could be quad tree, uniform grid, KDB, or our tree, and so on and so forth. The below is an example of what it looks like. There are different strategies, different ways it would be like useful for different use cases. And really the goal here is to put together the spatial partitioning and indexing all together. What that means is we're going to start with a bigger area. In this case, we're taking the continental US, segment it out and kind of cut it into like bounding boxes, right? And then using these bounding region, we build the high-level tree, the global index. That happens on the driver side of the Spark kind of job execution, right? And then further on, you're going to be looking at each of these boxes in the region and then having that the smaller grain tree getting built on the executor itself as you execute the Spark job. So as a result, you get a hierarchical kind of spatial indexing effect here and leveraging the same tree that was used for partitioning before in the earlier step. But this is not the only form of indexing, and a common strategy is using something like X3. What is X3? X3 is a system that is created at Uber a couple of years ago. It's open source there. It is a hierarchical, like hexagonal tiling system. The idea is as follows. You see at the bottom here, the smaller hexagon within a bigger hexagon in red. And then all of them made up like this surface that cover the entire Earth you see on the right-hand side. So why is that interesting? A really big part of this is the bucketing you can do about this. So you look at the map on the right-hand side here, you see like data point, they kind of go inside the hexagon. So instead of going in individual ones like separately, you can actually bucketize them into like one hexagon at a time. So you basically roll up all the numbers there, you can look at all that together. In individual hexagon. One of the advantages of hexagon is also equidistant. So you can see in the middle here, like it doesn't matter which direction you go, it has like the exact same distance when you are moving around. So transversal, neighboring, truncation, or even filling a region and filling an area, right? There's sort of different ways you can look at geospatial analysis using a system like this. So let's talk about truncation a little more. Truncation is a great way to look at like a small hex and then basically zooming out from that area, looking at the parent hexagon and so on and so forth. So the function is in X3 is called X3 to parent. Another approach is you look at something like K-ring. What that means is you take the hexagon kind of in the middle and then you kind of map out all the surrounding hexagon around it. So this is a great way to look at proximity and do like vicinity analysis. So leveraging X3 is like perfect for these kind of things. The reason why I want to talk about that too is like actually used within SafeGraph as much as it's also a foundation of the concept of place key. So I mentioned place key. The goal of the place key is to provide an easy way for any geospatial data set to reference the same physical place using a universal identifier to manage and handle challenges like address mismatches, fuzzy matching, all that stuff. And the encoding, what you see on the right-hand side, the where part is actually it's leveraging X3 index. And it was encoded in this kind of language where it's kind of easy to read and more legible. Moving further on, we're going to talk about use cases. So one of the primary use cases here is SafeGraph, is visit attribution. So you think about this particular use case here, you have a time series GPS signal, a person or device is going to a particular store. Now, if you look at the trivial approach of doing like intersection between radius and all these things, right? Like you would imagine in the bottom case, you're going to be wrongly attributing visit to the lower building, like that lower building here at the bottom. The way we deal with this in SafeGraph is the 3-step approach. Step 1, we do clustering on the time series geospatial data set that we look at. And then we apply a geospatial join to that data set, to that set of cluster, along with the building footprints. And then lastly, we take the result of the join, and kind of move forward with a prediction. So every single day we have more than like 2 terabytes of data coming through, processed using this way to compute the visit attribution. Here, I'm moving on to kind of like a handcrafted implementation of this. JTS is a very popular framework for geospatial, geospatial purposes. The way you would do that is you feed it the Vikit sort of like string, right? Basically a WKT format string. So we're using a WKT reader here in reading that data and generate a geometry object. And then secondly, we actually go build a str tree. What we do then is take all these geometry that we actually loaded and generated and insert it in the tree itself, and then broadcast the tree from the driver to all the worker. And subsequently, we leverage that tree that was broadcast in UDF and processing that data in that distributed structure. Now, you can imagine there are a lot of challenges with that. Like we're basically taking that very big, large data set, have to build it in one spot, have to distribute it all around. So imagine you don't have to do that, and you basically have to write a SQL query, and that does the same thing for you, right? So within here, you see at the middle, basically, you take 2 geometry and say, is one within the other, using ST with it. You can also do ST intersect as well, if there's not exactly so like encapsulation, but more like intersection. So you can tell it's much easier to use using that MM3 extension SQL syntax. And also to add, there's also spatial join you can write. The way this works is what we described earlier. There are kind of multiple steps. First is you take the data set and then you use the sampling to analyze it and create the tree structure. And then using that tree structure and say, I'm going to specify the tree type I want to apply for partitioning. And then you take the same partitioning scheme and apply to the second data set. And then lastly, you see at the bottom here is you're doing a spatial join between these 2 data sets. Another interesting use cases we have, an important use case we have, is computing geometry overlap. So what we do is take a high number of geometry we have, and then we want to process all of them and detect overlapping polygons. Very similar sort of problem we have is how do we do these analysis at scale? So we import all of these as a form of automatic QA. And also we could be doing ad hoc analysis, doing geospatial distribution analysis. Here's one example of it. So what you see at the top here is we're taking the polygons from the data set. We're doing some processing so we filter out certain like POI that we're looking for right now. And then we take some of these SQL function and take the wicket definition and convert it into geometry object, or computing the area from it. And then lastly, we take the data set and join it using the IDE, and then computing and detecting whether there are any intersection between the two data sets. And lastly, we use that information to compute the ratio of the overlapping area. And that's the result we're looking for in this kind of analysis. So lastly, moving on to architecture. So this is what it looks like. On the left-hand side, you see a bunch of data set we have landing from a variety of different sources. We're leveraging Delta Lake for versioning and updates capability. We take all of that and process using Apache Spark and Databricks. And at the same time, there's model that is part of the pipeline that we use Spark for training the data. We use human being for long tail, kind of like understanding long tail and edge cases and performing that annotation on the data set that feed into the training process. With Python and MLFlow, we manage the model deployment and then the model performance tracking. And then as a result of that pipeline, we feed it into an automatic QA system, also using Spark, that is hooked up to Slack, so we get notification when things happen. And at the same time, we also have a human in the loop like analysis to qualitatively check all the results coming from these systems. The result here is kind of pushed to the customer cloud you see on the right-hand side. So lastly, I want to point to the SafeGraph log. As you see here, we have very interesting information about how we're processing data. We see on the left-hand side, what sort of data sourcing we have, our expansion to a new region like United Kingdom. And then we also have a number of interesting use cases, whether it's investment research, right? Risk modeling, market analysis, market penetration, competitive intelligence, or just like how far people are traveling during the pandemic. So last but not the least, really want to state that we're really actively hiring a lot of interesting use cases. Please go to our website, safecraft.com, Korea, to find more information. And thank you for your time. Love your feedback.